Hello. I will be going today through my responses for the final for the Data 605 class. So starting off with problem one, as instructed, I've generated two distributions, one using a uniform distribution and one using a normal distribution, and then plotted them here. Moving to part one of the presentation, letter A. So yeah, we're required to estimate a number of conditional and joint probabilities. The first one asks us to estimate the probability that the random variable x is greater than lowercase x, its median, given that this random variable is also greater than y, the median of the y sample. Now, the key thing here is that both of these values, x and y, are the same, or roughly so. So we know explicitly that the mean of the normal distribution will be 10, and so we know that its median will be 10 as well. And for the uniform distribution, it ranges between 5 and 15, and so the median will be 10. Now we have some slight variance there due to random sampling, but that mostly rings true. They're both very close to 10. So if we know that x is greater than y, which is equal to 10, estimating the probability that x is greater than x, which is also equal to 10, should put us very close to 1. And we can check this empirically by first taking a subset of the random or the sample of x where it is greater than y, and then we can count the proportion of cases where x within that subset is also greater than x. And again, given that they're both equal to 10, we find that that probability is 1. Moving on to letter B, we're now looking at a joint probability that both x, the random variable, is greater than lowercase x, and random variable y is greater than its median, lowercase y. So I think the key thing here is that if we look at these individuals, these marginal probabilities individually, we know that because these are the medians, by the definition of the median, it represents the 50th percentile. So the probability of both of these is going to be 0.5. We can write it out to actually calculate it, but we can know that just from the definition of the median. And we know that the same applies to both x and y. Calculating a joint probability, we know that we can take both of these individual probabilities and just multiply them to get this joint probability, which gives us 0.25. I've shown how to kind of validate that two ways empirically, but I'll look at this one because it's involves just kind of random sampling. If we take a random sample from this broader sample 1,000 times, and then do the same thing with y, and we look at the number of cases where both of these conditions are met within that sample, the proportion comes out to 0.25. Finally, we're looking at the probability now that the random variable x is less than x, given that it is greater than y. Now we know from the first problem that where the opposite is true, where we're looking at the case where they're both greater than, the probability was 1. So if we're given that x is greater than y, and we're looking at the number of cases where x is then also less than x, if these are both equal to 10, then that should be 0. And we can confirm that by using the same framework from the first problem. We'll take a subset of the sample of x where this condition is true, that it is greater than y. And then within that subsample, we look at the proportion of cases where it is also less than x, and that comes out to 0. Moving on to part 2, we want to investigate this case, right? Really just kind of prove that the joint probability of this is equal to the product of the two marginal probabilities. And so we can explore that by building out this contingency table. I've just taken kind of subsets, laid out the conditions where these various conditions are true within the subset, and then use that to build out this contingency table. And so we can convert this contingency table into, from counts to probabilities by just dividing by the number of samples within these two samples, which is 10,000. And that gives us the proportion of cases where these things are true, which equates to the probability. And so if we look at this table, we can see the one of interest, which relates to x being greater than x and y being greater than y, is roughly 0.25, again, allowing for some random sampling variance. If again, we take the two marginal probabilities, right, that random variable x is greater than lowercase x, and the random variable y is greater than lowercase y, 0.5 times 0.5, as we showed before, comes out to 0.25. And so, yeah, I think with the contingency table, we show that the number of cases where this is true is equal to about 0.25% of the overall sample, which equates to the probability of being equal to the product of these two marginal probabilities. All right, so to move on to part 3, we want to look at two tests to assess the independence of these two random variables. So the Fisher's exact test and the chi-square test, in terms of similarities, both of them are meant to examine non-random associations between two variables. Basically, is there some kind of dependence between them? In the absence of these, any kind of non-random association, we can conclude that they are actually independent. Both of these tests take as the null hypothesis that the variables are independent, and the alternative is that they are not. And they both take a contingency table as their input. In terms of differences, I think the key difference to highlight is related to the sample size. So the chi-square test has kind of a minimum sample size. The rough guidance is that there should be at least 5 observations in each of the key buckets of the contingency table for it to be large enough to draw accurate conclusions. And by contrast, the Fisher test has no such requirement. And in fact, the test is designed to be used with smaller samples, although it's technically still appropriate for larger samples as well. In terms of applicability to our problem, the chi-square test seems more appropriate given that it is meant for larger sample sizes, but the Fisher test could be applied as well. And in fact, we have functions for both of those in R, and if we apply them, we get very close results. Our p-value is about 0.79, which is well above 0. With any reasonable confidence level or alpha, I think we would not reject the null hypothesis that these variables are independent. So we can conclude that they are independent. This is reasonable. It aligns to expectations given that we generated these two random variables with entirely independent processes and used two different distributions, normal and uniform, to generate them. All right, so moving on to problem 2. I start off by loading in the data that I got from Kaggle as instructed on this crab age data set. The first part asks us to put together descriptive statistics and histograms for each of the variables in the data set. And so I go through and put them all together, showing a summary of the distribution, kind of descriptive statistics, as well as a full plot of the histogram. And across all of these cases, we see some pretty significant skew. So for both length and diameter, we see left skew. And then really for the remainder of our variables, we see pretty significant right skew across all these cases. This also rings true for age, our target variable. The one exception really is the sex categorical variable is pretty well balanced across all 3 classes. The next section asks us to put together pairwise plots for at least 2 independent variables. So I chose height, weight, and length, those being kind of the key variables. There's some redundancy in some of the other variables, so I focused on these. And we can see that there is some evidence of a linear relationship, maybe between age and these variables. But additionally, we do see some pretty strong linear relationships between the predictive variables themselves, which is an indication of multicollinearity, which is something we'll need to address when we get to the modeling section. If we look at a correlation matrix for 3 predictor variables, we again see that there is pretty strong correlation across these. Again, this indicates multicollinearity, so we'll need to address that in modeling. We take this correlation analysis a step further and then put together a series of pairwise correlation tests to assess whether the true correlation between any variables is 0, and then provide an 80% confidence interval for the true correlation. And so with our initial test that we put together, we loop through all the different combinations pairwise of all of these variables. And in all cases, our p-value comes out to very close to 0. The true p-value will not be 0 because of just rounding in R. It shows as 0 in this column, but in reality, it's just very close to 0. In terms of our confidence intervals, we see that the correlation with age and all of the other variables is varies a bit. It's somewhere between kind of 0.5 and 0.7. But with our predictor variable pairs, the correlation in pretty much all cases is above 0.9. So we see that strong multicollinearity. Now the problem mentions, right, family-wise error. And because we're conducting so many of these pairwise tests kind of concurrently, we should consider about the possibility of drawing conclusions given the margin of error here. Basically, there's an increased chance of false positives, and those kind of compound as we conduct more of these tests concurrently. So there are some corrections that we can apply to give a more conservative estimate. One such adjustment is the Bonferroni correction, in which we essentially just take our alpha and then divide by the number of tests that we're conducting. Now, given that we had near zero p-values in all those cases, it's not going to affect the conclusion that we reached there, but it will affect our confidence intervals. So I've implemented that here. We see that our confidence level, we're now taking an adjusted alpha as our confidence level. And yeah, again, the p-value remains unchanged. We still conclude that the correlation for all of these is not zero, but we do see that our confidence intervals for the true correlation is a little bit different. They're a bit wider given our higher confidence level now with the adjusted Bonferroni correction. Moving on to the next section, we're going to take a correlation matrix and then perform some matrix operations on that. So I've started off by just generating this correlation matrix. I take the invert there to generate a precision matrix as instructed. With that, I can then take the product of that correlation matrix and the precision matrix and perform the LDU decomposition. Now, R doesn't have a function in place to do that decomposition automatically, but it does have one for LU decomposition. And so we'll use that as a starting point to get our lower and upper triangle components. We can then take this upper component and single out the diagonal of that to obtain our D diagonal component for the LDU decomposition. And then we'll take the diagonal of that D subcomponent to adjust the diagonal of the U component, right? We just divide by that, and that'll give us the unit diagonal for that upper component, which is one of the characteristics of this LDU decomposition. So we print all of those out here, and we can see, right, the upper triangle for the L component is zeroed out. The diagonal component actually just turns out to be the identity matrix, which we'll talk about why that is the case in just a second. And then our upper component, the bottom part, is zeroed out. To test the decomposition, we can then take the product of these three components and confirm that it reproduces or reforms our original product matrix that we had. And so I've printed out the original product matrix as well as the reformed matrix that is the product of those three decomposed components. And we can see that they are similar across the board, and actually just run a check to make sure that all the values are equal out to the 20th decimal place because there's some rounding there. And that match check comes back true. Yeah, so one thing to note, as I mentioned before, we see our diagonal matrix was the identity matrix. That's because of the nature of this product matrix, right? So we started with the correlation matrix, which is symmetrical and has just ones all along the diagonal. And so because of that, our LDU decomposition, the upper component is going to be equal to just the transpose of that lower component. And the diagonal is going to end up just being the identity matrix, right? With ones all along that diagonal. And we show that how that comes out here. We take the lower component and then we just transpose it to form the upper component. And then for the diagonal component, we just take a identity matrix of the same size. We print those out here and then run our same check with this alternative product, LDU decomposition, sorry. The product of those three components, compare that to the original product matrix. We run our check, and again, it comes back true, showing that these conditions run true for that, and still gives us components that we can use to reform the original matrix. Moving on to the next section, we are examining one of the variables within this CRAB data set using a parametric representation. And so I've chosen the weight distribution, which exhibits some right skew, and we're going to try and represent this with a parametric exponential distribution. Now, because this variable, actually the minimum value is above 0, we don't need to perform any kind of shift. We can go right into using this fit distribution function in the mass package to find the optimal lambda, which comes out to be 0.04 roughly. We can then plug that in to a random sampling from an exponential function with 1,000 samples to generate a kind of simulated representation of this weight variable. And when we plot that against the original one, we do see some pretty significant differences here. The overall shape is certainly different. And I think what's most significant is that the simulated version has some pretty far extreme values out in the right tail. The max going out to what looks like roughly 150, whereas the original distribution, the max value was less than 80. We can then move on to the next part of the exercise, which has us compare the 5th and 95th quantiles across both the parametric and then observed distributions. And then we generate a confidence interval for the mean of our observed distribution, assuming normality. And so if we put all of those together, again, the difference we highlighted before, which are kind of the difference in extreme values, is highlighted here. The 5th percentile is lower in the parametric distribution compared to the empirical one, as is the 95th percentile, which kind of matches what we saw in those histogram plots. Regarding the mean, we have a pretty tight band here between 23.3 and 23.5 roughly. The mean of the simulated distribution that we got from randomly sampling from the exponential is also 23.8. So it's just outside of this band, but it is relatively close to the estimated mean for our observed data. All right, so with that, we can move on to the final modeling portion. I start off by putting together a baseline model with all of our variables. We do see that they all appear to be significant, as does the overall model. We have a decent p-value of 0.55. But when we do our residual plot analysis, we see some potential issues. We see some kind of non-constant variance here in our residual plot. We see some potential non-normality as well in this residual plot, with some kind of far off values in both the left and right tails. And then we see a couple of really influential points out here. So yeah, there's some potential heteroscedasticity, it seems. And when we look at these influential points, nothing really jumps out. Most of the data points and most of the variables for these two data points align to kind of the first quartile of the distributions of each of these variables, with the exception of the shucked weight and the visceral weight. So it seems like the ratio between these variables and regular weight is a little bit off from what we see in the other data set, but there's nothing here that really indicates that this is like an erroneous observation or something that needs to be removed from the data set, at least at this point. So we'll keep an eye on these influential points and see if they appear in other iterations of the model. When we were looking at correlation before, we did see that there was a really high degree of correlation between our predictor variables. So I looked at the variance inflation factor to kind of assess multicollinearity, and we do see a pretty strong degree of multicollinearity across our predictors here. If we look at this adjusted variance inflation factor column, a number of these are above 5, which is kind of the rough threshold for when we think this may be an issue. So this is something we'll have to think about in future iterations of the model as well, how we might want to adjust for that. The first thing, though, is when we were looking at the distributions of these variables, we saw they all exhibited a good amount of skew. So I wanted to apply a power transformation to all of our variables and see how that impacted the model. So I've implemented that here. When we replot our variables, we see that actually they are much more normal now. And if we look at our pairwise plots, the linear relationship does seem a bit stronger. There does seem to be kind of some non-normality there as well, but I think the relationships are a bit stronger. We do, however, also see still strong linear relationships between our predictive variables, again, highlighting that multicollinearity. So if we refit the model with our power transformations, we see that most of our variables remain significant, as is the overall model. We have a decent R squared, or adjusted R squared, of 0.62 roughly. If we look at our residual plots, though, we do see some of these issues kind of persist. We see some kind of like an inverted U-shaped pattern in our residual plot. We see that there's some non-normality for sure, and these two influential points remain outside of the Cook's distance threshold here in this leverage plot. So given the persistence of some of these issues, I've decided for the final model to fit a principal component analysis to transform all of our predictor variables into this PCA space. So in the initial fit, we can see that right, the kind of drop off in terms of explaining a variance with PCA drops off really quickly. I chose the first three components. That gives us about 98% of the variance, which should explain a lot of what's happening in our target variable. So yeah, if we take that these three components, add back in our categorical sex variable, and then add back in our target variable, we can use that for some modeling, which I then fit here. We see that all of our variables are significant, as is the overall model, but our just our square is not great at roughly 0.48. When we plot the residuals, we do see, again, these kind of two outlier points. At this point, I think I decided to remove these 2 points. The residuals look a little bit better overall, but it seems that these two kind of outliers have persisted. Given that there wasn't anything really either way, and just the amount of data that we have, I don't see a major issue with removing them. So I took them out and refit the model and then compared the coefficients. There wasn't a massive change in these. Everything remained significant overall. Our R square increased slightly, so I left them out in the final model fit. Looking at our residual fits, we do see that these seem more random, which is indicative of homoscedastic variance here. Our QQ plot does indicate, that there's some, kind of far right tails in the residuals. This may indicate some kind of nonlinearity in the relationships overall, which we won't be able to capture in this linear model at this point. But yeah, overall, I think that the plots are much better. We seem to have a decent fit here, so I've gone ahead and used this as the final model. So I used this PCA fit to put together transformed variables based on the test data set. So I first scaled it, and then I applied the predict function to the initial fit with this new data, put that into a data frame again with the categorical sex variable, and then use that to predict values for this whole test data set. And then that's what I eventually submitted to Kaggle. Now I'll include my username information as part of the submission, but it gave me an instance score. My mean absolute error was 1.57. That sounds not terribly bad given the distribution of age that we observed earlier, but I'm curious to see how that stacks up with some of the other submissions. So that is all for my final presentation. Thanks very much for a great class, and yeah, I look forward to learning more.